So, as Bethany said, my name is Cate Levey, and I'm an R&D scientist at Blue Planet Systems. Thanks for having me here today. I'll be talking about chemistry and how I combine that with material science for climate applications. The goal of Blue Planet Systems is to store billions of tons or gigatons of CO2 in the built environment. So we're doing that through chemistry and then creating strong materials out of it. So I'll today go over a bit about my career path and how I ended up where I am today, and then I'll go into an overview of Blue Planet and how we use biomimicry to make strong materials from CO2. I'll then get into a bit of the process of how we make those carbon negative building materials and some of the science I'm working on with different crystal forms of calcium carbonate. So I started my career journey at Emory University in the Department of Chemistry. And my first job in industry was at Georgia Pacific. Georgia Pacific is where I really was first exposed to this intersection between chemistry and material science, and where I fell in love with composite materials. So there, my job was to synthesize adhesives for plywood and OSB, or chipboard. And I was doing these synthesis reactions of phenol formaldehyde thermoset resins. And what was really enthralling to me is that I could make changes to these polymers at an angstrom or nanometer scale and see that reflected in the properties of these building materials at enormous scale, like meters scale, and how the chemistry of those binders was playing into something as big as a building, and how we could engineer these building products by knowing about chemistry at the molecular scale. So from there, I went to Impossible Foods in 2014. At this time, the country was just starting to realize that the food system was really broken, but no one in the public discourse, there was not yet an awareness of the link between diet and climate. And I was really inspired by the vision of Pat Brown, the founder, to take things that people were already eating, so it didn't require behavior change, and to use science to make them healthier and better for the planet. At Impossible Foods, I was working on the material science and texture of the burger and helped create the texture of the first and second generation Impossible Burger. This involved a lot of looking at the material properties of proteins and other biopolymers to be able to match the target properties of beef, not only when it's cooked, but we had to match the material properties when it was raw, so it has to be soft and formable, and you have to be able to shape it into not only a patty, but also meatballs or whatever other form factor you might want to cook with. And then as it cooks, it needs to gradually turn from red to brown, and it needs to have a change in the fat. So the fat needs to leak out, and it needs to cook in a little puddle of its own delicious grease. And at medium rare temperatures, it should be soft and tender and juicy. And then if you keep cooking it at a well-done temperature, it also needs to match the material properties of a well-done burger. So we were looking at those different biopolymers and proteins from a material science lens to see how we could utilize those to match those target properties and achieve those thermal responses all the way along that really wide spectrum of textures. Then in 2021, I was hearing a lot about how the climate goals could now not be achieved without carbon capture and carbon removal. And so I decided to join Blue Planet Systems, where I am now. And that's what I'll be spending the rest of the talk on. At Blue Planet Systems, we are creating carbon negative building materials. So this is a photo of our product. It's a calcium carbonate or synthetic limestone, rock and sand. And we use that to create very high density carbon storage in the built environment in concrete. So Blue Planet is looking to nature. How does nature store most of the CO2 and the carbon on Earth? And how can we use science to accelerate that and be able to store even more carbon dioxide in our products? So we're making calcium carbonate, and calcium carbonate is the chemical formula for limestone. Calcium carbonate is 44% by weight CO2. And to make it into a solid that's very, very stable and can be permanent and stored forever as a solid, won't be re-released, you need to add a calcium and you need to add alkalinity in the form of here in the form of oxygen. So how we do that is we start with a byproduct from another industry that has high concentrations of calcium and alkalinity. Right now, we're using crushed concrete. So this is a waste product that would normally either get landfilled or used for very low quality applications. We put it through our process and extract those chemicals that we need out of it. And that waste concrete can actually then be upcycled to create a circular economy, and it can be used for higher value applications than it would otherwise be able to be used. So the waste concrete goes in, basically we extract the chemicals that we need out of it, and then it can be reused again in another building in a circular economy fashion. We then have CO2 that's coming from a pollution stream, and we contact that with our special carbon capture solvent, and we precipitate out calcium carbonate when that CO2 interfaces with the high calcium and high alkalinity solution. So how does this relate to concrete? We're making those rocks that I showed on the previous slide. Well, you hear a lot about concrete being a high emitting material. That carbon emission from concrete comes from only 10 to 15% of the concrete, which is the cement. The aggregate is a word for rocks and sand that actually make up the bulk of concrete. So the mass of concrete is around 70% of the mass of aggregate is about 70% of the mass of concrete. And by making carbon negative rocks and sand, putting them in the concrete, we can actually offset the cement CO2 emissions to be carbon neutral or even carbon negative, and create carbon negative or carbon neutral building materials out of it. And the really exciting thing about this is that we are making aggregate that is 44% by weight CO2. That means that we can store an enormous amount of CO2 in the built environment. The current aggregates market is around 55 gigatons per year, and that's growing. Humanity is emitting around 40 gigatons or billions of tons of CO2 per year. So you can see that if we used calcium carbonate that was made from CO2 emissions, that would unlock a reservoir for permanent safe CO2 storage that is 24 gigatons or billions of tons per year, and that renews every year. So this is really the biggest and the biggest storage for CO2 that needs to happen at this enormous mass scale on the billions of tons scale. Concrete is actually the second most used material on Earth after water. So my title's a little messed up. Okay, so how do we do this? Usually rocks take millions of years and high temperatures and high pressures to form. We need to figure out how to make strong materials that have strengthened by the time they leave the gates of our plant. So to do this, we look to nature. We have a lot of systems in the ocean, such as coral and such as shellfish like lobster and crayfish, which are making calcium carbonate that's very strong on a very, very rapid time scale. So we look a lot to see in nature how can we use a biomimetic process, which is analogous to the ones that are used by these organisms to make these really strong materials really, really quickly at ambient temperature and ambient pressure. So we are looking at some scanning electron microscope pictures of some lobster calcium carbonate. These should be CaCO3, it's calcium carbonate. So some lobster calcium carbonate and some blue planet calcium carbonate on the top. You can see how the microstructure and the morphology of those is very similar. And then on the bottom and on the right, we have coral calcium carbonate, tropical ocean oids, and some blue planet calcium carbonate. You can also see how our materials that we are synthesizing are biomimetic and are able to match the morphology of the calcium carbonates that are formed in nature at these rapid time scales where a lobster might shed its exoskeleton and then need to have a strong one again within a matter of a couple hours. So the process for Blue Planet is that we have these crystal forms of calcium carbonate where we have calcium carbonate as a polymorphic material. That means that the same chemical is able to be in many different crystal structures. So we have an amorphous or kind of randomly oriented calcium carbonate at the top of this Gibbs free energy diagram. And then as we go down to more stable crystal forms, we have vaterite, that's a metastable form, and then the two stable forms of calcium carbonate, the two stable crystal structures are aragonite or calcite. So we are looking at these different crystal forms and trying to understand how our calcium carbonate, as it first precipitates, transforms from solution and nucleates into amorphous particles, and then transforms from the unstable, amorphous, and vaterite phases into the stable and permanent CO2 storage states of aragonite and calcite. And looking at a material science lens of this, it's not only which crystal forms they're in on sort of a like angstrom to maybe nanometer max scale. We are also interested in the structure of those crystals at different length scales. And we're interested in how not only the chemistry affects that, but also the processing and the how the structure property relationships are playing with each other to form the final performance of that calcium carbonate aggregate product. So for this, we employ a pretty wide variety of different analysis techniques that you might expect for crystallography. We use XRD, FTIR, UIC, IC, TGA, but I think the best thing to show in a talk like this is the scanning electron microscope pictures. So here I have some SEMs of calcium carbonates that we've synthesized in the lab. And you can see here a really wide variety of morphologies amongst these different polymorphs. And even within a single polymorph, like say if you have vaterite or you have all aragonite, these are all the same chemical. And even within one polymorph or one crystal structure, you can also have different morphologies and different microstructures of those calcium carbonates. And this is really interesting to look at in relation to those different length scales that I talked about on the last slide, and what are the drivers for the amorphous and vaterite, the less stable forms, transforming into the more stable final forms that are permanent, and how can we manipulate those transformations to go the ways that we want so that we have better control over the process and the product, and tuning the structure property relationships to make the best quality products that we can. So that's how we sequester CO2 in the built environment. Thank you to you all for listening, and thanks to all my collaborators and mentors at both Impossible and at Blue Planet. Any questions?
Thank you so much for that talk, Cate. We have one question that someone asked about if you could say what the carbon capture solvents you used were. I suspect that information is proprietary, but I'll see if you can answer it.
Yeah, we're using an ammonia-based system.
All right. And then we have another question. What is the method used to extract calcium from the waste concrete? Do you use acid? Go ahead.
I decided to skip over that in the talk because it was going to take too long. We just use a countercurrent reformation process, and with the solvent that is able to extract it pretty well. And I think that's all I'll say at this time.
All right. And then I wondered, you've used material science in so many different fields, and I was wondering, are there other global problems you think would benefit from looking at with the material science lens? And if so, what are they?
Oh, yeah. I think this is one of the things that really draws me to this intersection of chemistry and material science, is that I see chemistry and material science all around me in literally everything I pick up, right? Even even paper is chemistry and material science. And so I think this is a really creative opportunity to be able to engineer lots of different products to contain CO2. So many of the products that we use on a daily basis are made of carbon, and there's a lot of different companies out there. Most of them are pretty small at this point, but looking at how we can utilize CO2 in a more circular fashion, circular economy, and make things out of it like plastics and like biological composites. One example is compostable plastics, right? That's made from agricultural products and utilizing plants to do the carbon sequestration, and then permanently storing that carbon that's been captured by the plants. There's also a lot of people working on being able to do that in a more technological fashion, and hopefully they'll make a lot of progress and we'll have more green energy to be able to scale those up in the future.
All right. Thank you so much, Cate. I really appreciate your talk.